Interlisp D is a personal computing environment. Environments have a number of characteristics. Perhaps the most salient is the presence in the user's office of the machine itself. Xerox, Dolphin, these machines, typically the size and color of a small cabinet, tend to sit in one corner of the user and give off heat and noise. And for that reason, they're increasingly now mounted remotely, not the person is using them. And this particular machine is usually mounted remotely, except on occasions like this where I have it photographed. To compensate for the very individualistic nature of everybody having a machine of their own, the machines are all linked together using some kind of communication network. In this case, it's the Xerox 3 megahertz research Ethernet network. And using that Ethernet network, I can reach out and access facilities that there's clearly no reason to have in my office. Things like shared file servers, shared printers, and the consoles of my friends and colleagues. The consoles themselves are also distinctive. In a conventional keyboard, they have a high-resolution bitmap display, which allows the use of very flexible graphics in presenting information to the user. In addition to the display, they have a pointing device or a mouse, which by sensing horizontal motion on the table, point under software controlling the object on the screen. The combination of very flexible input and output devices and the steady supply of computing guaranteed by the dedicated computer allows a style of interaction which is quite different from what one is used to in a time-shared environment. It's much more reactive and it has a much higher bandwidth through to the user. And one of the key problems in personal computing has been to develop techniques which exploit this power. Techniques such as window menus, browsers, graphic simulations, icons are all different ways to harness this power. As a result, when you look at a system like this, what one is most interested in is the techniques that are being used to communicate this information, the pictures that are being drawn. And for Interlisp D, that's a very sad misperception. Because in addition to being a personal computing environment, Interlisp D is also Interlisp. And Interlisp is a programming environment and language which has developed over the last 10 years on large time-shared machines like PDB-10s. During the course of this development, in addition to standard paraphernalia of a modern computing language, it's also developed a very extensive collection of programming tools. These tools, and the size of the collection can be best judged by the size of the Interlisp manual that documents them, have been proven to be very useful when people are trying to deal with very large programs that that are almost too large for them to understand and control. The kinds of tools that are provided are things like knowledge-based program analysis, automatic maintenance of databases about the files, programs, and where they belong, automatic error correction, and programmer's assistance. Now, the real challenge of Interlisp D for us was therefore to marry this rich tradition that came out of the time-shared environment with the specification, power, and flexibility of the personal computer. And what we're going to show you in this demonstration is the current state of the marriage between these two different traditions. Unfortunately, since we'll be demonstrating a programming environment, we're going to have to choose a very small-scale example in order to fit the example in the time that would be reasonable to ask you to watch. That's unfortunate because the real value of these tools is generally in coping with very large problems, and to work through a large or real problem in this time would simply not be feasible. On the other hand, we hope that the facilities we'll show you will give you a flavor for the kind of environment that's come from the marriage of these two different traditions and how they both contribute in their own way to simplifying the programming process. We're now looking at the screen of a Xerox 1132 running Interlisp D. As you can see, the screen is up into a number of rectangular or windows. Each provides a view onto a particular piece of data or activity. The graphical representations used in the different windows vary considerably, including text in a variety of different fonts, synthetic images composed by the user, straight and curved lines of a variety of types drawn by the system, and photographic images. This image at center right was generated by electronically thresholding a scanned-in black and white photograph. A variety of other techniques are available, including half-toning, for images with grayscale in them, like this one. In addition, the multi-bit per point facilities of these machines can be used to generate real grayscale images or even color photographs on an appropriately equipped display. There are a variety of different processes running in this system, and some of them are visible on the screen. The most salient is this one in the bottom right-hand corner, in which the system is solving the tasks recursively when it has nothing else to do. Further up on the top right, there's a time of day clock, which is updated continuously during the user's session. Finally, over on the far left is a traditional read eval print TypeScript window, into which the user types expressions which are evaluated and their values printed. We're going to begin our investigation of the Interlisp deprogramming tools by running a small program which is part of a system of linguistics programs at Xerox Research. This particular small program is editor. When I ran this editory program on the value of the variable pars, the system prompted me with a square to give it space for. When I press down the mouse button, the system indicates how much it requires and where to position it on the screen. When I do so, the system will take that space and put in that window a more graphically pleasing representation of the pars structure for what turns out to be the English sentence, "My uncle's story about the war will bore you to tears." In this window, the various nodes that represent nodes of the pars structure are active. When I point at them with the mouse, they lock onto the mouse and can be moved around, allowing the user to rearrange the layout of the tree on the screen. In addition, using a menu which comes up on this particular window, I can add or delete links or nodes, thus changing the structure, in this case to add a link between the noun phrase and preposition node. When I do so, those links, like the other ones, are moved around when I move around the node. In order to understand how this particular program is structured, the first thing to do is to interrupt it in the process of moving it. When I do that, by hitting the interrupt, a window opens on the right side, in which I have the facilities to look around and explore the dynamic state of my computation. The first thing that I need to know is how I got here. I can obtain that information by bringing up a menu of break package commands. In this case, I want the backtrace command, which will open up the left that indicates what the context happens to be. We can see here that starting at the top level, essentially I called the editor program from underneath the read eval print loop. A variety of different other programs, lattice, follow cursor, move node, until interrupted underneath the program. I can look at the status of any one of these particular programs by pointing at it using the mouse, and when I do so, the system will open up another window on top of the break TypeScript window, into which it will put the information it has about the particular stack frame that I pointed at. In this case, I'm asking it about the status of the particular frame cursor function. That function's name appears here. Its arguments, nd and ds, down the left-hand side, and their values over here on the right, and the local variable, in this case only one, called old pars. Old pars is fairly clearly an xy coordinate pair, but these two values up here are instances of Interlisp records or data types, packed representations of data, and not easily interpretable in this form. To look at them in more detail, I can select them using the mouse and then inspect them by running the inspector program on these. You open up a window to the left in which the system will put a more readable representation of this particular L node. In this case, we have the fields of that particular data type spread down the left-hand side, and their values in this particular instance are arrayed on the right. Some of them, like these numbers or positions here, are very easy for one to interpret. Others, like this bitmap here, are less clear from this particular representation. We can look at them, however, in some more detail by inspecting them in turn. In this case, when I ask to inspect that particular value, the system offers me a choice of looking either at its fields, information like how wide or high it is, or its contents, the actual bits themselves. I'm going to choose to do. When I do that, the system opens up in the center of the screen a bitmap editor window. The bitmap editor window gives me an enlarged view of that particular image, which I can change by adding new bits or turning them on, or taking bits out and turning them off. In this way, I can basically manipulate this image in a very convenient form, while the system continues in the top left-hand corner to show me what that image would really look like, real size. When I've finished adjusting it to my whatever desire I have, I can go up and use the menu in the top of the window to determine what to do with the changed image. I can do a variety of different things. I can do the cursor, for example. Alternatively, I could put it back where I found it. In this particular case, I'm just going to quit out of the bitmap editor without actually having changed anything, because I'm not sure whether this program was capable of adapting to a bitmap that changes underneath its execution. In addition to being able to browse user data structures like these ones, I can also browse the system data structures. Here, for example, I can select this, which is a font descriptor. A font descriptor is a data structure that uses to control the appearance of characters that are written on the screen. In this case, this has a large variety of fields, not all of which are immediately obvious, but some, like the font style, its size, and the face style to be used, are relatively easy to interpret, and this provides the user useful information about the system data structures that affect the way his program is operating. Using these tools, the user can in fact explore through both his own data structures and the system's data structures and its dynamic state to get a very good model of exactly how the program happens to be operating at any particular time. When you're finished looking at something like this, by bringing up the series of break commands again, I can quit out of this particular pause and just resume the program as if nothing had happened. When I do that, you can see that the break windows disappear, and if I go back to the window, I can still keep moving this around, and it's as if my break had never happened. When I do this, I'm going to observe something about this program that's a little bit anomalous. When I move this node higher than the node that it's been linked to, you can see here that the line is still being drawn from the bottom of the source node to the top of the destination node, even when the destination node is higher than the source node. But that works fine if the destination node is lower. Higher, you can see that the line is being drawn through the label, producing this very unpleasing graphical effect. This is the kind of small change that one might find oneself having to make in code that one didn't write oneself in order to use it, for example, if one decided to use this system to lay out arbitrary lattices rather than just trees. To make this change, what we're going to do is to interrupt the system again and start exploring its static rather than its dynamic properties. Interlisp provides a variety of tools to do this based on the master scope databases, which contain a complete static analysis of a user's code. In this particular case, I'm going to begin my exploration by asking the system to show me all the paths of calling relationships, starting off with the function edit tree, which is how I entered this subsystem. Using the information in the database, the system will build such a calling graph representation and invite me to give it some space to display it to me. When I do that, you can see that in this very compact representation, because these trees can get to be very big, the system has displayed the output edit tree. It calls three functions in subsystem: tree layout, edit, and graph node. These call a variety of other functions, and so forth all the way across, showing a complete map of the entire system. Nodes indicate nodes that appear in more than one place in the graph, possibly because they're closely. At any stage of the particular representation, I can use function names like this one here, and when I do, the system will actually get the source code and show it. In this case, down to the bottom right, the system has opened up a window into which it is going to go and obtain the source code from the file server and display it to me. source code. Note the system didn't actually have the source code loaded. It was compiled code. In order to get this, the system had to consult a database it contains about, for every compiled function, whereabouts the source code belongs. In this case, in the file latticer, every source file it knows not on this, just this local machine, but local Ethernet, that particular file stored. In this case, it obtained this source by looking inside the file phylum list users, which is a file on a directory on the local file server. Using these particular systems, one can walk over a subsystem, picking up pieces of code until one forms how it works. That's fine if one has a fairly general set of understandings in mind. In this case, however, we need some more specific. Going back to the script window, some specific question about who calls the draw between. Draw between is the system line drawing, and by who calls it, we can start narrowing in on who it is that might be drawing those lines incorrectly. For example, in this case, we're told that the only function that calls draw between. So therefore, link will be able to make a change that should affect the way it's drawn in the case that we've found anomalous. Back to the browser window, find the function showLink is right beside the button buttoned up. With a different mouse button, I can instruct the system to find its source code, but rather than just showing it to me, to load it in so that I can redefine it to change. Code comes back from the system will gray out the calling structure window to indicate that that particular calling structure is no longer to be trusted since showLink has been redefined, and will open up a window, an editing window, into which that code will appear. In this window, I can point to elements of structure, like a particular atom or this list. But it's not a character-oriented editor, it's a character-oriented one. So this out here is not something I can point at with the mouse. Over on the series of commands in this continually active, which I'm currently pointing at, so that whenever I push the mouse and makes that change. In this particular case, what I need to do is to draw between expression, which is what showLink does, between something in its first argument and something in its second argument, that by an expression which is conditional on the relative positions of the two arguments. To generate that conditional, I actually have to type it in. When I first hit the keys, the system opens up a buffer window underneath the edit window into which my keystrokes are collected. The particular keystrokes I have in mind are the expression, if the from node is above the to node, then basically I'm content with things the way they are. So I'll use this place marker to mean it's okay as it is. Otherwise, it's not okay as it is, but it's very nearly okay, so I'll start off with the same thing in both arms of the conditional. Simply by going over to the Edit menu and buttoning Replace, I can replace that draw between with a conditional expression now. Now, both arms of the conditional are still the same. They're both copies of what was there before. And in order to switch around whether I'm drawing from the bottom or the top, in the case where the from node is not above the to node, I'm going to take these from pos and to pos fields and switch them. And now I have a new piece of code that more reflects what I have in mind. I'm now going to exit from this editor, and when I do so, I'll be back inside the break TypeScript window on the far right-hand side. The system has told me, for example, that it has unsaved the definition of showLink to reflect the changes that I've just made. And from now on out, showLink will be running as interpreted rather than compiled code. I still have the version of edit tree that I was running suspended behind me, and I can go right back into it and see whether my change works simply by releasing this computation with the OK command. When I do so, I can move back over here into the edit tree window, point at this node, and try and move it. When I do, something remarkable happens. First of all, the node went away, the first step in moving it. But nothing else happened, and the reason for that can be seen in the TypeScript window immediately above the edit tree. The system has found, inside the function showLink, the name FRD, which it doesn't know anything about. It knows that's an error, but furthermore, in addition to knowing that it's an error, it looks around in the immediate context and uses its knowledge of Lisp programs to figure out that that's probably a typographical mistake for the atom FRND, which is one of the arguments to showLink. The system wouldn't make that change by itself because it may be wrong, but it's proposing this to me as a spelling correction that it should make inside my code. When I tell it that I want it to go ahead and make that change for me automatically, a number of things will happen at once. Firstly, the edit window you saw here grayed out because a change has been made in the code, and the system knows that that code is represented in that window and doesn't want me to look at that window and have an incorrect idea of what the code actually says, because it's just been changed. Then the system proceeded with the computation after having made that spelling correction and ran into an error which caused this window TypeScript to come up again for this break window. In particular, I'm broken inside the function above. I can see how I got here by bringing up another backtrace, and you can see here that I'm underneath the function showLink, having just called the function above. Now I can find out what the arguments are for the function above by bringing up the break menu again and pressing that command at the bottom. The system then tells me that above expects two arguments, position 1 and position 2, and they're currently bound to these two L nodes. Now that makes my error obviously immediately. Above was expecting positions, which was going to compute a coordinate relationship between. Instead, it was given L nodes. So my mistake was that I called above on nodes rather than extracting the positions from them directly. This is obviously a mistake I made in the change that I made in showLink, a second mistake. I can go and actually correct that by asking the system to run the editor again on the function showLink, this time invoked by typing in the edit command directly. This will bring up the window again. The window has been cleared, and you can see in here the system has repainted it to take account of the fact that this typo I made has now been corrected. I have to correct it again, however. This from node shouldn't be the node itself, it should be a position. Now there are a variety of ways of extracting a position from out of a node. Luckily, draw between also takes positions as arguments, so this expression here will extract a position from this particular from node, so that would in fact be a reasonable thing to use instead. So I'll replace that from node by a call on from position of from node. Likewise, to node, I'm going to extract the analogous thing using this call on from position, and that's in fact going to be much more like what I want. Having corrected that error, I now go over to the edit operations and exit from this particular call on the editor. And when I do so, that's going to put me back in the break TypeScript here. Bear in mind that all the time I've been doing this, that the suspended broken computation is still sitting there underneath me, waiting to be resumed. Now, in fact, you can see the status of that computation here. It turns out that everything was fine up until this point. It's showLink where the mistake was made. So what I could do now is, having changed showLink, would be to back out of that particular call to showLink using the revert command, and then restart it with a changed definition of the code that I've just finished making in the editor. This can be done by letting the computation proceed with the OK command. What I do, coming back to the edit tree window, you'll find that when I start moving this NP node now, you'll see that everything still works fine. I've got the old behavior back at least. Now when I move it higher than the prepositional phrase node, you can see here that the link is jumping. When I go up on top, it's going from the top to the bottom. When I go below, it's going from the bottom to the top, which is exactly the behavior that I wanted to have. At this stage, having successfully made this change, I can quit, leaving this call on edit tree for the first time since we first began this demonstration, and ask the system what the state of my files is. I've made several different changes. The system has kept track of those, and so it's capable of knowing that all of those particular changes were in the function showLink, That function belongs in the file latticer, and therefore latticer is the only file that needs to be updated. This information is maintained automatically, so at this stage I can basically save all the changes I've made and rebuild my world to a clean state by simply typing cleanup. It's in fact this kind of bookkeeping that the Interlisp system provides that provides programming tools that increase the programmer's productivity.
Channel 5 News at 10, the #1 primetime news hour Los Angeles. Now, Larry McCormick, T.U. Lee, Steve Rowe with Sports Page, and the entire Channel 5 news team.
Still lots more ahead today on News at 10, the Saturday Night Sports Page, with our special Olympic update, a revolutionary new way to score music soundtracks. And we'll tell you how female singing groups of the 60s influenced the music of the 80s. Film and TV music composers face a few problems that other composers don't. The mathematics of tempo become very complex when you have to match your music to an edited story. But now there is a computer that can get past the math to the music. Rick DeReyes has more.
The soundtrack behind a film or TV program is something we take for granted, yet it's important in setting the mood of the scene. Putting it together is usually tedious work for composers, but recent innovations have made it a snap.
I listened to him because he didn't hire some girl to follow me around and keep me busy while he was cheating me.
He told me.
Now, shows such as CBS's Knots Landing are using computers to help them make the mood. This innovation is the work of two brothers, Ron and Richard Grant. Ron, who scores Knots Landing, had always worked with film scores the way most composers do, using a set of math tables to help calculate each musical cue. But after working with his brother Richard, a computer systems designer, they came up with a radical new Auricle, a system that composers exact calculations in a matter of minutes without using all that computer language.
In the Auricle program, you ask the program to give you a timing, and then it gives you the tempo.
Since Auricle was first used last September, other composers have found it to be a time saver that lets them really concentrate on creating a score. Among its users, composer Bill Conti, the man behind the music of Rocky, The Right Stuff, and most recently, the background music for the Summer Olympics.
All I have to do is look at one screen and do a couple of little simple applications. I can't add, I can barely read, but with just a couple of moves, I can get all the information that I need real quick.
Just like the changing nature of computers, the nature of the Auricle is always changing. It's already been adapted for use with legal research, and eventually its creators see an even greater role for it, such as having it direct an orchestra and playing the musical instruments for it at the same time. From Sherman Oaks, I'm Rick DeReyes, Channel 5, News at 10.
What we're looking at here, what it appears to be, a computer. In fact, it's a Apple II Plus, unmodified, except for a bit.3 80-column card. Otherwise, it's as much of an Apple as any Apple you might buy off the shelf, except for one difference. And that difference is that this Apple, the software we've installed in it, installed, I mean simply right now loading off one of the floppy disk drives you might tend to see on the right, is an Apple that can handle three-dimensional textual displays in a fashion that's much more superior to that of Smalltalk, the Xerox Star, the Apollo domain system, and recently the recently announced Corvus concept. Of course, the Apple's a low-resolution screen, and We can't do the kinds of graphics and textual mixtures that the other machines can, but I think you'll see here by the rapidity of the motion on the screen that we have something that no one else has managed to develop yet. Now, what we're going to come up with first on the screen here is what we call the Auricle. Now, at the moment, this may not have any great significance, but after we show you what we've developed here on the Apple, we'll take you over to a Hewlett-Packard, and I'll show you an Auricle in operation. For the moment, consider it a channel through which one communicates with the system that's been developed. Now we're going to bring up a few more, what some people call windows, we call bays. We'll bring up another one, and we'll bring up another one. Now, what's interesting here is you can see that the other one is behind the one over there. For those of you who are patriots, that I think is the American flag. And then we'll bring up some more, and again, and again, and again. Now, take out one here that doesn't seem to have any text in it. Now, this is a demonstration program, and at the moment these are items that have just been constructed for purposes of displaying the three-dimensionality of the software we've developed. The critical ingredient here is you can see that just with an Apple computer with a 6502 processor in it, you can achieve tremendous animation speeds otherwise not achievable even on some of the more sophisticated devices. It's totally soft. To give you an idea, let's move some of the display around here, and we'll take and move one of them to the right. Now, what I'm doing now is simply hitting a key. We've defined R for right, and D for down, and L for left, U for up. On the system we would ultimately install these on, the software on, we probably use something akin to a joystick, a touchpad. There are a number of ways this might be done in order to execute it in an effective way. The best thing is not to use the keyboard, to use some kind of a natural, kind of continuous control device. We'll move it to the right here, and we'll move it down, and as we get closer to the screen you can begin to see just the dimensionality involved. I have it tied into the repeat key, and then you can see here, and then we'll move it up, and then we'll move it down to the bottom. Beep just as when it hits the margins, and then we'll go up again and go around. Now I can take and I can, let's say, curse one of the other ones. Let's curse one that's back, and we'll go right. Now let's watch this one go up, and you can see as you get closer to the screen that it goes up behind the items, and then down. Oh, my hand's in the way. And left, and then right, then up, and then left. Now the number of, we also have here an interim memory which at the moment keeps track of the last few thousand keystrokes that have been performed. And as I press it, you'll see it simply repeat the things I've done before, in reverse order, however. Now you notice how fast it's going. This is assembled code working on a straight Apple that has no bitmap screen. The same technique, virtually without modification, but simply accounting for the lower level bit structure of graphics, can be used to merge graphics with text three-dimensionally and to, of course, manipulate what might be called graphical information, photographs, charts, airplanes, matrix structures, what have you. In a three-dimensional way in relation to text, mix them completely, and the number of, I believe, planes that are represented at the moment is 8 or 9, but effectively there really is no limit to the number that we can represent. We can take and do one more example here to show you now it's doing, I'll set up a few things in the middle. Go right. And then I'll take and move another one down. Move this right. C02, and we'll move this one here to the left a little bit. I should use a repeat key, take up less space, or less time. And then move that down a notch. Then clear it, and then let's see if I can't get this thing to do about 360 here. We'll move it down, right, down, right, down, right. We'll go right, 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 right. You can clear them, by the way, and then take them off, bring them back up, take them off, back up, take them off, bring them back up. We'll move it right some more. And we'll move it right, up, right. Let's take it down one or two notches here like this. Do it again. And then depths on the other ones. And then we'll move this left and stop it at roughly the same position it started in. Now watch, if we hit the playback key here, you can see that it'll moves and floats around. Now many people, when they see this, think of it as a game, and actually, since it is a prototype and not linked into anything useful, it's hard to imagine what purpose the system may have at first, but then if you step one step down, you can conceive of almost an infinite number of possibilities. Of course, people who developed the Smalltalk language saw an infinite number of possibilities, I suppose, but there's a lot of them they missed. Obviously, for example, you can see in the background, this is a Westlaw page, which is the banner for the Westlaw Legal Research System from the West Publishing Company. If we assume, for example, that that's a case report, then we can, let's clear a few of these off here for the moment. And I'll show you C03. And suppose this is a case, and we're reading the case, and we don't seem to understand some crazy legal term that might appear in it. Well, using the Auricle to communicate with the system, we'll type in a request to see, for example, Black's Law Dictionary at a certain entry. And the system then would be able to display, without obliterating either the communications device or channel, and without obliterating the material you're using as the base reference, and then would simply call up and display the dictionary definition you wanted. If it was in the way or a little bothersome, you could turn and just move it out of the way, read it, appreciate it, not appreciate it, and when you're finished with it, you can get it out of the way. Believe me when I say the possibilities are infinite. Now, we do have an application for the system. It does not have as the prototype we worked up. It's worked up on an HP 9845 and is a universal communicator. It's a prototype, but essentially will allow any computer using the program to talk to any other database system in the world. It uses the Auricle as a communications channel, and will fade out and then we'll fade back up, and we'll show you the operation of the two-dimensional technique in an animated way in a system that's actually in use in a law office here in Los Angeles. As promised, what you see now is a Hewlett-Packard 9845T. At the moment, this device is the hardware which runs a law office management system, and that system was first put into operation in this office back in June of 1979. The first version of this device we had was the 9845A, which was first announced by Hewlett-Packard back in late 1977 or early 1978. As you can see from the screen, when the system is not being used, it displays a clock by the use of what is fairly well considered to be the sophisticated graphics ability of this device. As you can see in the upper left-hand corner of the screen where the clock is displayed, it says press any key, and you can get the system menu. The system here is a basically sound menu-driven series of programs, and this is the highest level menu, and you can see that selection number 4 is the research subsystem, and we'll select that now. Requires my initials for identity and then a code for entry, and as I press that, it will access the research subsystem I mentioned in the previous demonstration of the Apple II computer. It is getting the program off of a Winchester drive, which is produced by Hewlett-Packard, which is off camera at the moment. And you will see shortly the copyright notice appear. We call this program Bailiwick, since it was initially designed to be used in law offices for research, not only for legal research purposes, but generally too, for dialogue, the New York Times, and what have you. The system is really quite generic. It is totally soft and database oriented, and when fully implemented will allow anyone using the system to define any specific library. For example, as you can see by entry here in this, I will define a library as the legal research library, which is called Westlaw, and using the input bay here, which we call the Auricle in the Apple demonstration, you simply indicate to it what the library is, and it will now go out to the mass storage devices and set itself up to communicate with the Westlaw legal research system. Now, ordinarily, we would then designate either Telenet or TimeNet in this circumstance for the sign-on, but since that can get rather expensive, we'll just put into a test mode, and at that point it needs a clearance from yours truly. And clear me here at this point. And then I will set it into a test condition, at which point it tells me at the lower left-hand corner of the screen that the test file assigned as samples, and the digits indicate the particular platter on which the test files occur. Now, what I did about a month or two ago was simply record about 2 hours worth of actual legal research I performed on the Westlaw legal research system. Now, as I hit the run key, the system then sees itself communicating with the drives, and in will come the Westlaw banner. And there we have the Westlaw banner. Now, it is really from the development of this system that we came across the algorithmic technique for the display of information on planes or three-dimensionally, somewhat in the neighborhood of the Smalltalk system. And as you can see, I'm moving what we call the input transom or input bay or Auricle around the screen. If it's in the way, you can simply clear it. Now, unfortunately, Hewlett-Packard designed this device to be essentially a closed system. It runs on their HP Extended Basic Language, and they do not provide the documentation necessary to get into the hardware in order to write an effective assembly language or a series of assembly language routines which might be used to speed the process up. It also limits our access to the hardware in such a fashion that we can, in this sense, only really employ 2 planes for our purposes. But you can see that the one we do use, which is the Auricle, is essentially really powerful. You communicate not only with the Westlaw system. For example, here, this would normally call for a password, and I'll just, put in a series of numbers and anything at this point and transmit it. If I transmitted it, the comm line's not active, and it would normally go out the port through the modem and cause Westlaw to send back the next response, which you'd see as follows. You'll note that incoming is coming in the lower left-hand corner. That would ordinarily be the second transmission from Westlaw after you had identified yourself by use of the password. Now, this program, in a fairly brief way, demonstrates the use of the Auricle or the communications channel to the system. What makes it so powerful is that no matter the focus, the topical focus of your research in this particular instance, or, for example, program development in another instance, no matter that focus, you can now have the ability to communicate with the system in an extremely anecdotal fashion. For example, if you don't like the direction of the status line, no matter what you're doing, no matter your research, you can put in instructions such as this, which would reverse the status line and cause it to move in the other direction. If you wish, you can, there's a recall key I've defined here, and you can actually cause it to go the other way. When the copyright notices goes on about every 5 minutes, it obliterates the display line for a moment, comes back with local time, and then reverse, moves in the reverse direction. If one would want the status line to go faster, of course, you just tell it to go faster. This is essentially for demonstration purposes in a way, because while you're doing one activity, the Auricle or this particular communications channel permits you to do any other activity, whatever you prefer at that particular point in time. Many people want to know whether it gets larger. Of course it gets larger. It's simply a question of how you want to deal with the system. It's very effective for formulating queries for Westlaw. Unfortunately, we can't drive it much faster since we have to work through the interpreter in the system, which HP developed. It's a very sophisticated basic language, but in some applications can be rather slow. You can just clear it out for the moment, and you can do that. The Times Square line below tells you the status of the system, whether data is coming or going, the time of day, often used to answer any questions that the system honors when talking to it. If you want the local time, for example, you can type that into the system. Also tends to demonstrate how you can request things that are not within the current topical focus. Now, the important thing to notice when comparing this to the Apple, for example, is that the type of software we've developed employing the technique is essentially machine independent. Neither the Apple nor the 9845 has any special hardware attached to it that allows it to take advantage of these particular techniques. The three-dimensional algorithms we developed are very unique and not only operate to compress the procedures involved in allowing you to maneuver information in this way, but actually operate to compress the information itself. That's precisely why it works so fast. The actual algorithmic technique itself is compressed and consumes, for example, in its more sophisticated fashion on the Apple, no more than 900 bytes of machine code. It is sufficiently independent that it could be implanted not only on firmware as a kind of a Dolby-like device in order to three-dimensionalize virtually any computing system, but can also be used in software programs to three-dimensionalize them. For example, VisiCalc could have moving columns so that they could be adjusted and dealt with. It's a marvelous approach to information. Many people just like to watch the input bay disappear. Just for the sake of by the way, we store the pages locally, and you can stack them and bring in the old Westlaw manner. And another demonstration of the two-dimensionality can be seen in the status line, because we can take and move the status line up a notch or two, have a repeat function, and you can see below that the status line moves here from right to left, pardon me, and as it moves over the information below it and passes by, the information is not obliterated and is picked up as the status line moves on its way. Now, with the full three-dimensional technique and the Auricle, we can do all kinds of functions, as you saw on the Apple. In this system, we cannot call up, for example, the codes that Westlaw requires in the formulation of its queries in a three-dimensional way. However, on a system that gives us access, no matter the hardware, but yet gives us access into its operating system and into its hardware itself, we can then create a multiple of planes or depths of information and give to anyone, ultimately, who might use a computer the right to be as organized or as cluttered as they wish, rather than to have the way they use information dictated by systems designers and programmers who often have no real touch with the types of professions and uses that the actual consumers might put to a given computing system.
like 30 seconds to 30 seconds to animation. How did you get it to keep going like that? How can you
don't know the end of it.
Remember, it's never downtime.
In about 8K, about 20,000 moves.
Remember, it's 20,000 moves.
Really? In this particular, I had to find a piece of music for that.